Hello all, and welcome to the first of the Intrigued Engineers tutorial videos. I've put this together as when I was getting into PLC programming, my first port of call was the online forums, which can best be described as just a hot mess of confusion. Following this, we got the trusted F1 key, and granted it goes into a lot of depth and it is really good, but it's one of those catch-22 situations. It only really makes sense once you know what you're doing. But bear this in mind because we will be touching on it later in the video. So I've made this video for people like me with no formal training in TIA Portal, but they just need to find a solution to get the job done. So speaking of which, you click the link, you know why you're here. Let's be honest, it's a pretty niche video. It's not going to be hitting the trending page anytime soon. So today we're mushing together a Siemens 1214 PLC and a CB 1241 comms module insert and getting that to talk to a Modbus Simulator that is running on my absolute unit of a field laptop. That's the dull hum in the background. I'm hoping my microphone's not picking up. So let's get started with the wiring. How do we put this thing together? Right, so here I've drawn out the schematic of how I've wired my module up. At the top we've got the 1241 module, and underneath is my RS-485 to USB converter. We're setting it up in what's called a half duplex or 2-wire mode for the RS-485, and to be clear, RS-485 is the actual wire and hardware side of stuff, and Modbus is the protocol or language, if you will, that will be talking over that RS-485 connection. As you can see, we've tied the TA and TRE terminals together, and the same on the B side, as there's some internal resistors in the 1241 module that we want to make use of. These wires go to the A and B terminals in the RS-485 to USB converter. The M is for the common ground, and you want to connect this to the ground of whatever you're communicating with. You may be able to get away without doing this, but especially here where I am, we got a lot of earthing and grounding issues, so it's kind of a must. Here you can see my actual connection. I got the TA, TRE, TB, and TRB connections all on separate twisted wires, and as well as a separate connection for the ground. In this example, we're not going to be using any ready to send signals, so I've left the RTS connector unconnected. Here you can see the termination in the USB device with the TA and TRE wires into the A terminal and the TB and TRB wires into the B terminal. In this setup, the little orange wire sticking out there is my ground. Like I said, the earthing situation here is a bit of a nightmare, so I've gone absolutely OG in connecting the ground of the module to the chassis ground of the laptop. A final important note is something that took me ages to work out. I bought in a cheapo RS-485 to USB converter, so for one, there was no ground connector, and secondly, and infuriatingly, the A and B terminals were mislabeled. So for the hawk-eyed among you, you may see I have my TA and TRA wires actually going into the B terminal in this case, and vice versa. Not going to say how embarrassingly long it took me to work that one out. Okie dokie, so that's the wiring sorted. Wasn't that fun? Now let's get into the guts of her and get this programmed up in step 7, or TIA Portal, and down with the kids. Okay, so let's get to the programming side of stuff. So I'm going to start us off in a completely clean sketch, but the first thing I'm going to show you is the Modbus Simulator. So I'll put a link in the description to where I downloaded this from. But we're just running a holding register here. So we've got 10 values in here from 0 to 9. Got most of them static. I've got the first one just iterating just through some numbers so we can actually see that we got a live communication going on. For the setup, using slave ID 1, like I say, we're using a holding register, and this is going to come into it. So the address here is 0, the PLC address is 40,001, so remember that. Quantity 10 is just the number of these guys. That's about all you need to really know for this initially. We're running it on a half duplex setup, so we don't have any request to send or anything like that. So, oh, it is connected, there we go, I left that on. So in here, serial port, this is just my USB to RS-485 converter in there. So I'm running at 9600 baud rate, 8 data bits, no parity, and 1 stop bit. Again, like I say, no RTS or anything like that enabled. And we're in RTU mode, not ASCII. So there we go. That is all set up and running. Good. Let's get to the guts of the stuff. So it's a completely clean build. I wanted to show you it this way just because just the way I like to set it up, just so you're not kind of overlapping memory bits with clock bits later on. But that's just me, so if you're better than me at this, feel free to do it in a different way. So I'm going to add a new device, and this is going to take a while to load sometimes, so I might just pause this for you and go in super fast motion. Find a PLC. Pro tip as well, because I've got a bunch of different analog inputs and outputs on there, rather than having to specify them each time, if you come down here to unspecified PLC, I mean I'm running a 1214 system, find the unspecified version of that, click OK, and then when it comes up we can just auto detect all the stuff on there. It saves you a job having to find all the right serial numbers and versions of the right analog inputs, outputs, digital inputs, outputs, what CM board you have, all of that good stuff. Oh my god. Oh, there we go, that was fun. Right, so as it's unspecified, we're going to go to detect. I gotta make a coffee. Here we go. So have a look over the Ethernet. Now I've got my laptop directly plugged in to the PLC. So it's found a thing. Simple Modbus. Good. So it's found all that. Detect. And because it's found it, it should auto detect all the extra I/O I've got on there. Ta-da! There we go. So you can see I've got 4 extra modules on this side and the actual CB1241 itself on the front there. So what I'm going to do, oh my god, it's still loading. There we go. Is pull up this guy to get the information for him when he loads. Here we go. So in the general, first thing we want to do is in protection and security is come down here when it wakes up. There we go. And we're going to turn on permit access to put gets. So that's one. And then you don't have to do this, but I find it helps a lot, is enabling the use of the system memory byte. So turning that on. There we go. And also the clock memory bits. And just me being me, I always overwrite these things when they're low, so I like to put them out of the way. So just put 1000 in there. It's only 4, and then this next one's 8, so we can set that as 1001. Fan-dabby-dozy. So let's open up our program blocks. We're just going to do this super simply in the main. You can make it as complicated as you like afterwards, but for now we're just going to do a lot of hard coding in there just to give you an idea of how all this goes together and how all that stuff works. There we go. So here's our main program. Now, like I say, I'm not formally trained in this, so if anyone's got any comments as to why something works in a certain way, then please get in touch, write in the comments. I'd love to know more. But what I found with the CM board that we're using, it won't actually take this Modbus RTU blocks. I just have not been able to get it for the life of me to communicate with that. So I've been using these older functions down here. So what we're going to need anyway, before I digress too much, is a COM load and a COM master. Now the COM load we want to run just once, so we're going to give it its own instance of a data block. COM load we only want to run once when the whole program starts up, and then the master's the thing that loops and acts like a master, reads or writes to the holding register, the input register, output register, whatever we want it to do. And we're going to give that its own data block as well. Fantastic. Kind of looks like we know what we're doing. So for all the stuff down here and here, I'm going to come to in a minute. First off, I'm going to make just a data block itself, just to hold all the stuff on this side and keep it all nice and tidy. So I'm going to add a new block that's a data block. Just leave it called data block. And I'm going to add the names of everything down here that is on this side, and I'll get back to you in 2 shakes of a lamb's tail. Okay, we're back. So, like I mentioned before, I've created this data block. Inside it is mostly bools and some words, just to take the output from these blocks, just so we can utilize it in other stuff. But like I say, we're going to keep this really simple, so we're not really going to use most of it. So just going to put them in here. So I'll probably speed this bit up because it gets a bit boring. Okay, so now this is all done. We have everything coming out of here and pointing to somewhere in this data block on this side. So basically all this means is when something happens and this load block is done, we can get a signal to know that it's done, and when it throws an error, we can see it's throwing an error and what the status of that error is. That helps us to debug later. So the request, this is another reason why I like to initialize the clock bits at the start, because there's 2 ways you can do this really. There's something called first scan and initial call. Initial call, sometimes I just found it just doesn't work for me. I don't know why. If you know why, please let me know. That sometimes when on startup it just misses its initial call. But the first scan has never actually failed for me. So you can see here the M1000.0. So that's one of the memory addresses that we initialized when we first started everything up. So we'll pop him in there. So this should just get 1 request the first time it starts up. The port, if you come in here, click there, and then just find the port that we're using. So like I say, you know what video it is. We're attaching a CB1241, so there it is. Click him. Done. Baud rate, as I've already said, is 9600, general standard. Obviously, your stuff might differ. I'm using 0 parity. The MBDB. Now, we want this to point to this instance here. So what we want to do is just come on here. If you just start typing, there we go, MB Master. So what we want to do is put it in there and then click none, because it adds this little dot for if you want to go into subsections. We don't want to do a subsection, so click that none. Now I have noticed in some other blocks that there's a bit of a bug in some of them, and it, even when you click none, it leaves that dot in there and it can throw up some errors. So there we go, and we can see DB2 there, DB2 there. We're happy. So that is our load block done. For our master, we're going to come to the rec in a minute, but the MB address, as I said before, in the slave that we're using, slave definition, our slave ID is 1. Now, we're just going to hard code it in here as 1, but obviously if you've got a whole bunch of things on the bus with different addresses, you use a bit of code to loop through there and iterate through all your devices, but we're keeping this super simple. That's 1. Now mode. This is where I want to talk a bit about the F1 button. So if you click anything and press F1, you do get a very good help menu. But like I said at the start, it's only really good when you know what you're doing. Might have to give this a little while to load. There we go. So we're in. So I clicked on the MB Master, pressed F1, and we're in. And this gives you a kind of description of everything. So what the rec is, MB address, and it does this for any block, and it goes into a lot of depth on everything. These are very, very helpful, because if you're anything like me, when you get into something, it'll be throwing out all manner of error codes. So you can come here, read across the error code, and start trying to get a bit more information about where you're going wrong and try and fix it. So what we want to come into here to do is to have a look at this mode function. So the mode, click on him. Now, if you're used to Modbus and just getting into it from Siemens side, this is where it gets a bit weird. So we have our Modbus function calls here, we should be used to. So 1, 2, 3, 4, well, you know how to count. The mode itself in Siemens is a bit different. So if we want to read an output bit, it's mode 0. If we want to read an input bit, it's mode 0. If we want to read a holding register, it's mode 0. It's all the same. So basically reading is 0, writing is 1 or 2, depending on whatever you're doing. But what the Siemens software actually does is it takes your mode and it takes your Modbus address that you put in, and it works out from your mode and address what actual function it's going to put in and fire down that cable for the actual Modbus communication. So as I said at the start of the video, we're wanting to start off from reading a holding register, which is this guy here. So we want to have mode 0, and we want to be reading address, well, starting at address 40,001. So if we go back into the code, so change that mode to 0, data address, as we can see in here, we're starting at offset 0, which in reality is 40,001. Data length, again, we put this in before, so 0 to 9 is 10. And the data pointer. So what the data pointer is it points to the area of memory where you want to read from, write to, or what it's going to look for to do something with the data. So we're going to make a new data block. And on purpose, I'm just going to call this register. I'm going to show you one of the things that really tripped me up when I was trying to get my head around this initially. So what I'm going to do is just create an array. What should we call it? Whatever. We're going to create this as an array of integers. Nope. Anything but that. And we're going to make it an array of 10 integers. Look at that. Boosh. There we go. So that's all set up. All of these have a starting value of 0, so we know where we're starting from. And now if we go back to this, we want to point this data pointer to that register. So we come in here, have a look for a register. There he is. Click him. And we want to point it to the array, but we don't want to point it to a particular byte in that array. So when we get to this bit, we don't click on the individual bits, we just click none at the top. Again, it hasn't put the dot at the end, so that's all working okay. Press enter. Now this is the crucial bit, because it all looks good, but if we ran this, it'd be throwing up errors left, right, and center about invalid data pointers, but we've put it in there. So what's the issue? And again, if you know more about this, lots of people know a lot more about this than me. Please get in touch and let me know why. But what we have to say is, register block. Right click him, go to properties. In the properties, in attributes, we need to disable this optimized block access. And when we disable that, we get this little warning message, click OK, click OK. And now it can actually look at that memory address and point towards it, write data to it, and read data from it. Why? I don't know. But yeah, it works. If it works, it's not stupid. So the only thing left we've got to do is to do this request pulse. So what I'm going to do is utilize the fact that we know when this is done. So I'm not going to build in any sort of error recognition. You can do that off your own backs later because it's just simple logic. But what we're going to do is create an AND gate in LAD, which is just 2 of these because I'm old school. And we're going to put in what date is it in? It's in data block. So we have a look in data block, and we want to have a look when load is done. So when that is true, we want that switch closed. And for this bit, because we've initialized the clock pulses as well, we can come in here and start typing clock, and we can look and say, clock 2 Hertz. There we go. So this is going to be pulsing 2 times a second, but it's only going to get through to fire the request when this block is done. And that is that. That should work. So this is now where we need to come to uploading it to the actual PLC. So for uploading it to the PLC, does cause a lot of weirdness if you just go straight up here and download it straight to the device. Because this is a brand new install, what we want to do is come up here to the PLC 1, right click it, and before we do any actual software uploading, we want to do hardware. And we want to do, well, let's just do it in 2 bits. Oh, that's compile, sorry. So download to device, hardware configuration. And this is probably taking age to get its act together again, so there might be a bit of fast forwarding in the edit. Oh no, here we go. So Ethernet connection, start the search. So it's found it. So we're going to load the hardware. I'll come up with a whole bunch of stuff. Basically say yes to it. There we go, load. Fantastic, so we've got our hardware configuration up there, and now we want to put up our software. So download to device again, software all. And here we might have to actually tell it needs to stop and take a breather while this comes on board. Here we go. So yeah, no action, we need to tell it to stop. And then we can load it. Fantastic. So this should all be working. So we're going to go online. And we're going to monitor this. Impossible. Oh, I mustn't have started it properly yet. Wait for all the greens. There we go. It is running very slowly today. Now we can monitor. Here we go. So we can see on our load, the first scan will have fired. Done is true. That's good. Error is false. That's very good. And then the 16 hashtag #000 just means no errors. So I'm a happy man. Coming down to this, you can see because this is done is true. This is true, and now we'll be firing this at 2 times a second. The refresh rate of the monitoring isn't that quick, so it's not really picking up that it's 2 times a second. And the done will only be true for 1 scan in this thing. So again, we're not going to pick that up on the refresh rate, but we can see we're not throwing up any error codes. Our status is no error. Everything's happy. So let's go to the register itself. Have a look at what's going on here. So monitor, and these values, if I've done my job right, should match what is happening in the holding register, and it is, which is a relief. There we go. Okay, so that's reading to a holding register. How do we write to a holding register? Well, using what we've just learned, it's super simple. We'll go offline, have a look at the help. Always good to just cross-check this. So that was reading to a holding register. Let's try and write to a holding register. So we come down here, writing to a holding register. That's what we want to do. The actual address is the same. So 40,001, 40,001, same register. But we need to change mode from 0 to 1. So I'm just going to do a bit of housekeeping in my Modbus Sim, so that's not auto incrementing anymore because that just causes all sorts of naughtiness. I'm going to come down here, change this mode, hard code it to 1. Like I say, feel free to make that a variable. In fact, it'd be pretty poor if you didn't make it into a variable, into a bigger program. But yeah, we're just keeping this super simple for now. We're going to re-download that. We've already done the hardware stuff, so now we can just throw up this updated file. We haven't changed anything massive. So there we go, that's all happy. And if we go online again and do some monitoring of what's going on in our registers, when it wakes up, here we go. So what's actually happening now is we're writing whatever's in here to here, and shock horror, they're both the same. But if we come in here and change this 8000 whatever to 2, you can see in here, first register has changed to 2. There we go, 2. Hours of fun. There we go. So that is how you read and write from a holding register from a Siemens PLC. So I hope that helped. Keep an eye out for more videos from me coming out soon. Wanting to do a load more around industrial applied engineering, so should be fun, if that's your bag anyway. So for the first time, thank you very much for watching.